Hi, I've had a couple of questions about one of the problems on the assignment that related from chapter 2 that related to something called Simpson's paradox. So I've decided to give you a little YouTube on that. So what I'm going to talk about today, let me give you first of all the overview. What is Simpson's paradox about? Basically, Simpson's paradox is a situation where you get results from a test that seem paradoxical. And the reason they seem paradoxical is that, as you'll see in our case, you'll have a treatment that's better for the men and better for the women taken as separate groups, but when you lump them together into a total group, it's actually overall the other treatment is better. So it's a worse treatment. So what's going on there? What conclusions should we draw from data like that? And yeah, so what is actually going on in that situation? So let's look at an example. I think an example is a good place to start with any mathematical problem. So I'm going to imagine an example, and this is hypothetical data, where I've got two treatments, treatment 1 and treatment 2, and I apply it to a population of 1,000 men and 1,000 women. So, but I don't randomly assign the treatments, okay? And it's important that I'm not randomly assigning them, because if I were, what's about to happen would never happen. What's going to happen is that 100 men are going to opt for treatment 1, and 900 men are going to opt for treatment 2. And of the women, exactly the opposite. 900 of them are going to opt for treatment 1, and 100 of them are going to opt for treatment 2. And this is really where the trouble starts. Okay? We shouldn't have something like that going on, but we do. So now let's see what the results are. So what I'm going to do is tell you, of these 100, how many of them responded favorably to the treatment. Okay, so of the men, 50 men responded favorably to treatment 1. So that's a 50% response rate, favorable response rate. And of the men, 540 responded favorably to treatment 2 out of the 900 who tried it. So I'll just put in brackets that that's a 60% response rate, favorable response rate. So what that means is that the winner, as far as the men were concerned, is treatment 2. Okay? Now, let's look at the women. So for the women, 900 of the women took treatment 1, and of those, 720 responded favorably, and just so you know, that's an 80% favorable response rate. And of the women who took treatment 2, 90 of them responded favorably, which is obviously a 90% favorable response rate. Okay? So far, so good. So again, the women, 90 is better than 80 for this favorable rate. So again, the women seem to do better with treatment 2. So both the men and the women do better with treatment 2. Okay, so far we're going along hunky-dory and no problems, right? So now when we get to the total, here's where the problems start. So for treatment 1, there's 1,000 subjects totally, and 770 respond well, so that's a 77% favorable response rate. And for treatment 2, there's also 1,000 subjects, and 630 respond favorably, so that's a 63% response rate. So if you look just at the total data, treatment 1 seems to win. 77 is better than 63. So what's going on? How can that happen? How can treatment 2 win for the men, treatment 2 win for the women, but treatment 1 win overall? And faced with confusing and paradoxical data like that, right, what are we supposed to conclude? Alright, so what's really happened here is there's something that you might not notice if you don't know to look at it. And that is that if you look at the men's favorable response rate, whether they take treatment 1 or treatment 2, it's in the 50s and 60s. Whereas if you look at the women's favorable response rate, whether they take treatment 1 or treatment 2, it's in the 80s and 90s. So what that means is that women do better to either of the treatments, respond better to either of the treatments, for whatever reason. They're responding better to either of the treatments than the men are. So what that means is if for other reasons that we don't know, they opt for treatment 1, that's going to bias our total results to treatment 1 because there's more women taking treatment 1 and they do better whatever treatment they take. So it biases the experiment. So that's why we really would have wanted to do this properly. We would have wanted to randomly assign people to treatment 1 and treatment 2, and that way we'd know there wouldn't be any bias that was confounding the result, which is what's happening here. There's a bias among women. Well, the women are preferring treatment 1, and women do better to either treatment, so that biases the outcome. And so what that means is that in this case, and in many cases, this more precise drilled down data is actually more accurate. Why? Well, because this tells you that for these smaller subgroups where the population is, at least we hope, uniform, we have improvement in both cases. Right? It doesn't matter that for the overall we have treatment 2 doing better in both cases. It doesn't matter that for the overall treatment 1 does better because that data is messed up. And it's messed up because women who do better to either treatment have preferred treatment 1, and that's biased the results in favor of treatment 1. Okay, so that's basically what's going on. Now, I want to mention that I saw a quite dynamic guy talking on YouTube about Simpson's paradox, and in his case, he described a slightly different situation, and he said that in his case, this was the right number, that you should be working with this number. And his case, instead of this being men and women, this was day 1 and day 2. All right? Now, he could be right, depending on how they ended up on day 1 or day 2, but I want to tell you what the critical thing is that would make this the right number. The critical thing would be if these two populations were identical populations in terms of their response to the treatments, okay? If they were identical and indistinguishable populations, so if, you just basically said we're doing 100 T1s, we're going to randomly assign 2,000 people to T1 or T2, we'll do 100 of the T1s on day 1 and 900 of the T2s on day 1, and then 900 of the T1s on day 2, and 100 of the T2s on day 2, and then we got these results, well, we'd say, oh, this is some kind of a weird fluke, really this is the right number. But that's because we randomly assigned them to the different days, and so the two populations were indistinguishable. Here, when it's men and women, they are different populations, and so it's meaningful that these people, or it's at least probably meaningful that these two did better than those two, right? That women tend to respond better. It wouldn't make as much sense to think, well, the people we randomly assigned to day 2 responded better than those on day 1. If they did, you'd have to say, is something else going on? I mean, it would make you wonder about the experiment. But there are some situations where this could possibly be the right number if these are really the same populations. But if they're not, absolutely, the drilled down specific data is the right one. Okay, so that is Simpson's paradox. And I hope that helps you with the problem that I've assigned on it. Good luck with that, and I'll talk to you soon.